A student planned to carry out an experiment to determine the enthalpy of reaction when magnesium metal displaces zinc from aqueous zinc sulfate. Student uses this method. A measuring cylinder was used to transfer 50 centimetres cubed of aqueous zinc sulfate into a glass beaker. So they've used a beaker like this and they've put 50 centimetres cubed of the zinc 2 plus the zinc sulfate in there. A thermometer was placed in the beaker. Okay, so that's our thermometer. And then they added 2.08 grams of magnesium powder and stirred it, and the maximum temperature was recorded. They got a starting temperature of 23.9 and a maximum temperature of 61.2. And then it asks us to show by calculation which reactant was in excess. So we need to calculate the moles of each of the magnesium and the zinc sulfate. And then we're going to use the data to calculate the enthalpy of this reaction. So this is kind of linking to required practical 2, measuring an enthalpy change. So we're trying to remember the practical procedure as well. We've got the specific heat capacity of 4.18 and we're assuming that the solution is 1 gram per centimetre cubed. So the first thing we need to do is work out which reactant is in excess, because remember we're only going to use the limiting reagent. So if we work out moles of magnesium, they gave us a mass of magnesium, so we're going to do mass over MR. So we look up magnesium on the periodic table. Calculate that on your calculator. 0.08559, so I'm going to round that to 856. Okay, so we'll get a number for the number of moles of magnesium. Now I'm going to repeat that and find the number of moles of zinc sulfate. Now for zinc sulfate, they gave us a volume and a concentration, so we're going to use moles are very clever, volume in decimeters cubed times concentration, because remember this is centimeters cubed, this is moles per decimeter cubed. We do need to get them into comparable units, so decimeters cubed from centimeters cubed. Type that on your calculator or in your head, you could do that maybe. We're going to get 0.05. Now according to the balanced equation, the ratio is 1 to 1, so to use up all that magnesium we would need a lot more zinc sulfate, which we don't have. It means magnesium is in excess, yeah. If it's 1 to 1, we wouldn't need to double anybody. So whoever's biggest is the one that's in excess. Magnesium is in excess. What that means is for our calculation later on, we should use zinc sulfate's amounts as our number of moles, because that's the maximum number of moles that could react. The next bit is to calculate the enthalpy change. Now enthalpy change is delta H. We can't get there directly because delta H is in kilojoules per mole. So first of all, we're going to calculate heat energy, Q, in joules by doing mc delta T. Now in this equation, the M is the mass of the solution, and the solution is actually the 50 centimetres cubed of zinc sulfate. Now because it told us the density was 1 gram per centimetre cubed, we're going to say that that is 50. And then we times by the specific heat capacity 4.18, and then we need to find the delta T. So if we just go back on our calculator, find the difference between 1.2 and 23.9. The delta T is 37.3 degrees C. Now, a lot of students think that they need to add this and turn it into Kelvin, remembering that 0 degrees C is 273 Kelvin, but you don't need to do that because this went from 23 to 61.2. This was a difference of 37.3. The difference is exactly the same on both sides of the scale. So we're just going to use 37.3. So we type that on our calculator and we would get a heat energy change. Oops, we've turned into an error. Heat energy change of 7,795.7. And that would be in joules because 4.18 was in joules per Kelvin per gram. We've times it by the kelvins and the grams, so we've just got an answer in joules. Now, our enthalpy change needs to be in kilojoules, so the next thing I would need to do is convert that to kilojoules by dividing by 1,000, so 7.7957 kilojoules. Then the next step is to find delta H, and delta H is kilojoules per mole, so Q over moles. Now remember, we wanted it in kilojoules, so we've turned it to 7.7957. And remember, the moles we use is the limiting reagent, because that's the maximum amount that could react. So again, we go on our calculator and we work out that that is 155.9. At this point, I'm going to round to 3 significant figures because it's going to be my final answer. So 156 kilojoules per mole. And then the last thing is that this was an experiment. We need to take account that the temperature rose during this experiment. So we're going to add in here a minus sign to represent that this reaction was exothermic. Minus 156 kilojoules per mole. And then it goes on and says another student uses the same method but got minus 142. And the data book value is minus 310. So our answer was minus 156. Another student got minus 142, but actually the answer was that 310 kilojoules per mole of energy were released. So a lot more energy was released than we're accounting for. What is the main source of error that could have led to this? Well, the main source of error that could have led to this, the reason that we're not getting as big a reading as we should, is heat loss. The solution was not just putting all of that heat into the thermometer, we were losing heat to the surroundings. Okay, so it was going into the beaker instead of into the thermometer, into the air around it, and that we weren't measuring it. So the number in the data book shows a lot more heat being released than we measured in the thermometer. And it says our question continues on the next page. Suggest how the student's method and analysis of the results could be improved in order to determine a more accurate value. Justify your suggestions. Do not refer to the precision of the measuring equipment. So that says that's telling us don't use a better thermometer with a more precise reading. So don't improve the resolution on the thermometer. Don't try to get a smaller degree of precision on that thermometer. And it says do not change the amount, so we can't reduce the errors by increasing the volumes and the masses to get bigger temperature changes. We need to improve the method that the student used. Okay, so we need to think about the required practical here. How, when you carried out an enthalpy change practical in your lessons, did you do that different to the student's method? So let's look at the student did. They put it straight in a glass beaker, put a thermometer in, measured the initial and the final temperature, and that was it. Perhaps when you did it, did you use some insulation of some description? Most students would have used a polystyrene cup supported in a beaker to provide additional insulation, perhaps with a lid. So did you improve the insulation? Did you use a better insulated reaction vessel? So maybe you carry out the reaction in a polystyrene cup, supported in a beaker that provides extra insulation, with a lid. Okay, maybe that's our first thing. And then perhaps think about how you analysed your results. Did you just do a final and an initial reading? Or can you remember that in this experiment it was highly likely that your graph ended up looking something like this? And then you found a temperature rise by doing an extrapolation and a temperature rise. So maybe you need to take some more temperature readings. So did you record the temperature for 3 minutes before addition of the magnesium? And then add the magnesium So 3 minutes gives us the 0, 1, 2, 3, 4 points of data that we can draw a line of best fit through. If we add the magnesium at the 4th minute and then record the temperature for a further maybe 10 minutes, so anything maybe more than 6 more readings would give us a good rate of cooling. So it gives us a good set of data to use to plot the graph and extrapolate. And then you could plot these points of temperature on the y-axis, because that was the thing that was dependent on your time that you were measuring. Okay, so we were changing the time and measuring the temperature. Yep, so we could plot a graph of temperature against time. And then what we would do is we would extrapolate the curve before and after addition back to the point where we added the magnesium. So back to the 4th minute. We could then read off the delta T, the temperature change, at the time of addition, at the 4th minute. For us, that's when we've said that we've added it. Okay, and this would correct for some cooling to the surroundings, because we're looking at the rate of cooling in the environment.